Hello students, welcome back. In this part, we will discuss more about voids. We know that voids are of two types, tetrahedral and octahedral. So let's locate these voids in any unit cell. Let's take cubic unit cell, CCP, and then we will discuss about the size of the tetrahedral and octahedral void. So which is bigger in size? Is it tetrahedral or is it octahedral? So the answer to this question you will get if you once you go through this particular part. So let's start. Now let's understand more about voids, about tetrahedral voids and about octahedral voids. How do we locate them? Okay. Number of voids filled. So whenever in ionic solids the packing takes place, the bigger ions, usually anions, they form the close packed structure, and the smaller ions, usually cations, they occupy the voids. They occupy the tetrahedral voids or they occupy the octahedral voids. Always the bigger ions, anions, they form the close packed structure, and the voids are taken up by, they are occupied by the cations. So if the latter ion is small enough, then tetrahedral voids are occupied. If bigger, then octahedral voids are occupied. So if the cations are small, then the tetrahedral voids are occupied, because the size of the tetrahedral void is less as compared to octahedral voids. So since if the cation is small, then the tetrahedral void is occupied. If it is bigger, then octahedral void is occupied, because octahedral void is bigger as compared to tetrahedral void. So not all octahedral or all tetrahedral voids are occupied. In a given compound, the fraction of the octahedral or tetrahedral voids that are occupied depends upon the chemical formula of the compound. Okay, so depends upon the chemical formula of the compound, the voids tetrahedral as well as octahedral voids are occupied. Okay, so first we locate, we understand more about tetrahedral voids. We locate the tetrahedral voids in a unit cell. Okay, so the unit cell, in this case, one cube can be divided into 8 small cubes as shown in this picture. So this is a bigger cube which I divided it into small cubes which are 8 in number. So 4 below and 4 above. So total there are 8 small cubes, and in all each small cube has 4 atoms. Yeah, each small cube is having 4 atoms, which is shown here. This is the small cube and it is having 4 atoms. So when joined together these 4 atoms, you will get a regular tetrahedron. So this is if you join these atoms, you will get a tetrahedron. You are getting a tetrahedron. Thus there is one tetrahedral void in each small cube, right? So because tetrahedral void is formed when the 3 spheres in one plane and one is placed above covering the void, right? So that is the situation exactly in this small cube. So there is one tetrahedral void here. I will show here where it is. Yeah, there is one tetrahedral void here. Okay, so but this is the such small cubes are 8 in number. So each small cube is having one tetrahedral site or tetrahedral void. So total in this big cube we have 8 small cubes. So total there are 8 tetrahedral voids. Each one is there in small cube. So this is 1 and 2, and in this cube we have one more. So 4 below and 4 above. So total we have 8 tetrahedral voids. So each of the 8 small cubes have one void in one unit cell of CCP structure. So this is what FCC structure. So in which each small cube is having one void. So total there are 8 tetrahedral voids. So now let's locate the octahedral voids. So let us again consider the unit cell of FCC. Yeah, this is the unit cell of FCC, where if you see, if I consider the atoms at the face centers, right? If I join these atoms, I will get a regular octahedron. So at the center of this one, I will have a octahedral void. I have one octahedral void exactly at the center, at the body center. Okay. So the body center of the cube, see, this is the body center. The body center of the cube is not occupied and it is surrounded by 6 atoms on faces. So this is one octahedral void, and Not only the one which is at the body center, we have more octahedral voids. So let's see what are those octahedral voids and let's locate them. So besides the body center, there is one octahedral void at the center of each of the 12 edges. So each edge is having a octahedral void at the center of it. So let's see that. Yeah, if I consider this edge, so this is one face center atom, corner atom and corner atom. So these four are belonging to this unit cell which is shown, and the rest two are belonging to the adjacent unit cells. So this is one and this is one which are not belonging to this, which are belonging to the adjacent unit cells. So but here at the center, here you can see, so you have 4 and one above and one below. So this is going to be our octahedral void, right? This is going to be our octahedral void. So each edge, at the center of each edge we have octahedral void. So total we have 12 edges. So we have 12 octahedral voids. But this void is not exactly, it does not entirely belongs to the unit cell, right? Because each edge is shared by 4 unit cell. So only 1/4 of it, 1/4 of the void is belonging to the one unit cell. Okay. So the one which is at the body center, which is at the body center, it belongs entirely to the unit cell. So total we have how many? So 1/4 into 12, which is equal to 3. These are edge centers and one at the body center. So total we have 4 octahedral voids, right? So in CCP we have 4 atoms. So that's why if the number of close packed atoms are 4, then octahedral voids will be 4 and tetrahedral voids will be 8. So the 8 tetrahedral voids we already seen. So let's see a video demonstration on, let's understand more about this, the tetrahedral sites as well as octahedral sites. So this is the cubical close packed structure CCP, ABC type. So where we have here the 3 spheres below and 3 spheres above. So there is one octahedral site at the center of here, and similarly we have a tetrahedral site in this position. In this position we have a tetrahedral site because there are 3 spheres, the 3 yellow spheres in above plane, and below that there is one. So we have tetrahedral site there. So in cubical close packed structure, total we have 4 atoms, right? Total we have 4 atoms. So the octahedral sites are edge centers. The one which is at the body center, right, which is shown in this yellow color, and all the edges, at the center of all the edges we have octahedral site. So all the yellow colored spheres are occupying the octahedral sites. So total we have 4 octahedral sites. So one for each atom. And let's go to the tetrahedral voids. Yeah, tetrahedral sites or tetrahedral voids. Yeah, you can see here, as I already told you, that you can divide this big cube into the 8 small cubes, and each cube is having a tetrahedral site at the center of it. So the green one, the green spheres, the green particles are occupying the tetrahedral sites, right? The green spheres are occupying the tetrahedral sites. So this is, yeah, one more. So these are all showing the each individual tetrahedral site. So total we have 8 tetrahedral sites. So the 8 tetrahedral sites are shown in this figure, 4 here and 4 here. Okay. So now we are able to locate the tetrahedral sites as well as the octahedral sites. So what is the size? What is the size of a tetrahedral void? What is the size of an octahedral void? So let's calculate that. So first we'll calculate the size of tetrahedral void, and then we'll calculate the size of octahedral void. Yeah, so here if you take, this is a cube that is used to understand and to calculate the size of the tetrahedral void. So in tetrahedral void we have 3 atoms in one layer, and in above that we have one more. So at the center we have a void, right, where you assume that a particle is fitting in that, and the radius of that sphere which is fitting into the tetrahedral void is say suppose R, and radius of these particles are say suppose capital R. The small r is the radius of the tetrahedral void and the r is the radius of the particle or radius of the sphere. Okay. So, these three spheres which are lying in one plane, and this is the sphere A that is placed above these three spheres, and in between we have this one. So, this is our tetrahedral void. So, this is our tetrahedral void. So, let us assume that the void is spherical, and we have to calculate the radius of this particular sphere. Okay. So, how we can calculate that? We can calculate that, it is not so difficult. So, these three spheres are in one plane, okay, and this is above. So, if you join the centers of these four spheres, you will get a tetrahedron, you will get a regular tetrahedron. So, this is having a radius r and this is having a capital radius r. Okay. So, let us consider this phase diagonal. This phase diagonal, right? So, this is edge length A and this is edge length, this is also A. So, this A, the length of AB, the length of phase diagonal AB is equals to what? From Pythagoras theorem it will be root 2A, root 2A, and these particles, these two particles are actually touching each other. Though in this figure they are not shown that they are touching, but they are actually touching each other. So, if they are touching each other, then the length of phase diagonal AB should become equal to 2 times of the radius of the particle. Okay. So, from here what you will get is r is equals to a by root 2. R is equals to a by root 2. This is the expression 1. So, let us call this as expression 1, and AD is our body diagonal. AD is our body diagonal. So, from the triangle ABD, where AD square is equals to AB square plus BD square, right, from the Pythagoras theorem. So, AB's length is how much? AB length is root 2A. So, it is 2A square plus BD is what? BD is edge length A. So, A square. So, it will become 3A square. So, AD square is equals to 3A square. So, AD is equals to what? AD is equals to root 3A. So, this is the length of body diagonal which is equals to root 3A. Okay. But here these three spheres are also touching. So, this sphere is touching this one and this sphere is touching this one. So, it is like this. So, this is a big sphere and this is the void and this is, so this is our A and this is our say D, right. So, like this they are touching. So, here since they are touching each other, what you will get is the center to center, the distance AD is equals to root 3A, which is equals to, this is R. So, this is actually diameter, that is 2R, and this is R. Okay. So, the distance AD is equals to what? The length AD is equals to 2R plus 2R, which is equals to 2 into R plus R. Okay. So, let us equate these two, which is equals to 2 into R plus R is equals to root 3A. So, from this what we will get is R plus R is equals to root 3A by 2. Okay. So, let us call this as expression 2. So, from these two expression you can find the correlation between R and R, that is the radius of the tetrahedral void in terms of the particle size. Okay. So, the first one is what? The first one is R is equals to A by root 2 is the first expression, and R plus R is equals to, what is R plus R is equals to root 3A by 2. This is the expression 2. So, just divide 2 by 1, divide the expression 2 by 1, what you will get? You will get R by capital R is equals to root 3A by 2, root 3A by 2 divided by A by root 2. So, A will get cancelled, you will get root 3 by root 2 you will get. So, which is equals to 1 plus small r by capital R. So, 1 plus small r by capital R, what you will get is, you will get 1.225, because root 3 is 1.732 and root 2 is 1.414. So if you calculate, you will get 1.225. From that, R by R you will get is equals to 0.225. So this is the relation between, the correlation between the radius of the tetrahedral void and the radius of the particle, radius of the sphere. Okay. So radius of the tetrahedral void is only 0.225 times the radius of the particle. Okay. So this is the size of the tetrahedral void. Just now we derived it. I hope that you understand the concept here. Here only what you need to know is, you have to know that in tetrahedral void there are 3 spheres in one plane, and there is one which is placed above touching these 3 spheres. Okay. So if you join the centers of these 4 spheres, you will get a tetrahedron, and at the center of the tetrahedron you have a void, you have some empty space, and that size of the empty space is equals to 0.225 R. Okay. So let's derive the size of the octahedral void. Okay. The size of the octahedral void. Yeah. In case of octahedral void, we have 4 spheres in one plane, and there is one sphere above the plane and one sphere below the plane. Okay. So one sphere above and one sphere below, you will get a octahedron, and at the center, if you fit in a particle, and the radius of that particle is, say, suppose small r. So here small r represents the radius of the octahedral void, and capital R represents the radius of the particles. We have the same convention which we used in calculating the size of tetrahedral void. Okay. So here this is even simple. It's not complicated like tetrahedral void, but it is even simple. In triangle ABC is a right angled triangle, right? Right angled triangle. So in triangle ABC, what we have is, we have BC square is equals to AB square plus AC square. So BC square is what? R plus R, 2R square. So 4R square is equals to, AB is how much? AB is AB, which is capital R plus small r. So capital R plus small r square plus capital R plus small r square. So which is equals to 2 times R plus R square, which is equals to 4R square. So 2 1s, 2 2s. What you will get is R plus R square is equals to 2R square, 2 capital R square. So bring this R square this side. So R plus R by capital R whole square is equals to 2. So which gives us R plus R is equals to, R plus R by R is equals to root 2. So which is 1 plus small r by capital R is equals to root 2 is 1.414. So from here you will get R by R is equals to 0.414. So the radius of the octahedral void is equals to 0.414 times the radius of the particle. Okay. So here you can see this radius is actually bigger, right? The radius of the tetrahedral void is how much? It is only 0.225 times of R, but it is 0.414 times of R. So that means the octahedral void is bigger than the tetrahedral void. Okay. So if the cation is smaller, then it will fit into the tetrahedral void, or if it is bigger, then it will fit into the octahedral void. Okay. So this is the size of the octahedral void as well as the size of the tetrahedral void. Okay. Let's go further. So the radius ratio in AB type structure. So if the radius ratio, the radius of cation by radius of anion, if the radius ratio is equals to, if it fall in this range, that is 0.225 to 0.414, if it fall in this range, it will be a tetrahedral structural arrangement, and the coordination number will be 4. Okay. The examples are given here, and if it falls in 0.414 to 0.732, the structural arrangement is octahedron and the coordination number will be 6 accordingly. So if it is greater than 0.732 and it is less than 1, then you will get the cubic arrangement, which is having the coordination number 8, and these are the examples which are given in this here. Okay. So let's solve some questions based on the concept that we discussed now. So it is given that in a cubic closed packed structure of mixed oxide, the lattice is made up of oxide ion, okay, and 1/5 of the tetrahedral voids are occupied by divalent X plus 2 ions, while 1/2 of the octahedral voids are occupied by the trivalent ions. Then the formula of the oxide is. So such kind of questions are very common in competitive examinations, and let's see how to solve this. It is given that lattice is made up of oxide ions, right? It is CCP, cubical closed packed structure. So the anions, they take the FCC arrangement, so the number of oxide ions will be 4 because it is taking CCP arrangement. Oxide ions are present at the corners as well as at the face centers. Now the cations are now occupying the voids. So since we have 4 oxide ions, 4 closely packed oxide ions, so the number of tetrahedral voids will be how many? Number of tetrahedral voids will be double, 8, and octahedral voids will be same, that is equals to 4. So let's keep this information here, and it is given that 1/5 of the tetrahedral voids are occupied by divalent ions. So X plus 2, they are occupying 1/5. So 1 by 5 into how many tetrahedral voids are there? 8. So 8 by 5. Number of X plus 2 are divalent cations are there, and the trivalent Y ions, they are occupying half of the octahedral voids. So half into total how many octahedral voids we have? We have 4. So which will be 2. So we have the formula X 8 by 5, Y 2, O 4. So let's multiply this with 5 to get all these subscript as integers. X 8, Y 10, O 20. Okay, you can simplify it further. You can write X 4, Y 5, O 10. X 4, Y 5, O 10. So C will be the answer. Okay, so this is the way to solve the question. Always try to solve this kind of question systematically. Write which are forming the lattice and which are occupying and what are all occupying the tetrahedral octahedral voids, and it is good if you write this information aside so that you don't get confused and you don't have to remember. So this is the first multiple choice question, and go to the next question. So if 3 elements X, Y, Z crystallized in cubic solid lattice with X atoms at the corners, Y atoms at the cube center, and Z atoms at the edges, so then the formula of the compound is. Options are, these are the 4 options that are given. So also do this question systematically. Let's write X, or first write X and then Y and then Z. Okay, what is the information given? That X atoms are at the corners. So we have 8 corners and each is having a contribution 1 by 8. So 1 atom of X is present effectively. Y atoms are at the cube center. So at the body center, which contribution is 1, and Z atoms at the edges. That means at the edge centers. So total we have, how many edges we have? We have total 12 edges, and the contribution of ion, which is contribution of the atom which is present at the edge center, is 1 by 4, since that edge is shared by 4 unit cells. So this is 3. So we have 1 atom of X, 1 atom of Y, and 3 atoms of Z. So X, Y, Z3 will be the formula. So C, again C is option. X, Y, Z3 is the correct option. Okay, so let's move to the last question, last MCQ. Select the correct statements. For cesium chloride unit cell, the radius of cation plus radius of anion is equals to root 3a by 2, and for NaCl is given. So void space in BCC is given, and void percentage in face centered unit cell is 26%. So let's select the correct statement in this, correct statement from this. So in cesium chloride, which is body centered cubic lattice, so cesium ion at the center and 2 chloride ions at the corners which are touching the cesium ion at the body center along the body diagonal. So this is radius of cation, and this is 2 times radius of anion plus, this is radius of anion, and this is radius of cation, and this is radius of anion again. So this length total is equals to 2 times RC plus RA, which is equals to root 3A. So RC plus RA is equals to root 3A by 2. So A is the correct option, which is perfectly right. So for NaCl unit length, this is given. So let's see. In NaCl, if you recall, the edge, if this is the edge, the sodium ion is present at the octahedral void and the chloride ion is at the center, which is touching the sodium ion like this. So here, so this is center and this is center. So this is the radius of chloride ion. So radius of chloride ion plus the 2 times the radius of sodium ion plus the radius of chloride ion is equals to the edge length A, because this is the edge, they touch along the edge. So 2 times the radius of cation plus the radius of anion is equals to A. So radius of cation plus anion is equals to A by 2. But here edge length is taken as L, so it is L by 2. So this is also right. So B is also right. So the void space in BCC unit cell is 0.68. No, in BCC unit cell the void space is 1 minus 0.68, because this 0.68 is the fraction occupied by the atoms. So the void space will be 1 minus that. So it will be 0.32. So this is false. The void space percentage in face centered cubic unit cell is 26%. So in face centered unit cell 74% of the space is occupied by the atoms, only the remaining 26% is void space. So the void space is 26%, which is right. So A, B, D are the correct answers. Okay. So students, in this part we discussed more about voids, tetrahedral and octahedral voids. We located them, and we also discussed about the size of tetrahedral and octahedral void, and octahedral void is bigger in size. This is the answer to the question which I raised you in the intro of this particular part. So now, how efficiently you can pack the particles in the volume given to you. That is, we are going to discuss about packing efficiency in our next part. So to know more about this packing efficiency, keep watching for my next part.